Okay, so it's my pleasure to chair this last session for today, where we'll have a block of 5 talks, 5 minutes each, followed by 5-minute questions and answers. And first talk will be given by MD Jahidul from University of Florida, and he will present SVAM.
Hello, everyone. Welcome to the presentation of our paper titled SVAM, which stands for Saliency-guided Visual Attention Modeling for Autonomous Underwater Robots. So the idea is to identify interesting objects and pixels in an image so that visually guided underwater robots can model its visual attention and make fast operational decisions, such as where to go, which samples to collect, and so on. Towards solving this problem, we adopted the salient object detection problem and proposed a novel deep visual model named SVAMnet. The SVAMnet not only achieves state-of-the-art performance, but more importantly, it provides platform-specific design choices. So it provides a full model for high-end GPU use and provides a light model for robot deployments. So our full model runs at 20 frames per second on 1080 GPU, and light model runs on 20 frames per second on Jetson Xavier. Here's an example of how we can use SVAMnet for real-time robot vision. Imagine we want to perform enhancement on a full-resolution image from robot's camera. We can use state-of-the-art models, but they run on very low input reception, so the output will be something like 256 by 256. To enhance all the patches, we need quite a few computational load, which is not possible on a single board device. So what we can do instead, we can run SVAMnet and look where the salient pixels are and only enhance the patches that we need. So SVAMnet runs on 46 milliseconds only. So depending on how big the salient objects are, we can get at least 2 times or up to 10 times faster processing. So now we'll briefly talk about our model architecture. So the backbone of the SVAMnet model is a traditional encoder-decoder model. So the input goes to 5 layers of encoders for feature extraction, and then those are used by reflective 5 decoders in a top-down fashion for saliency estimation. So we then use a residual refinement module to further refine the output for fine-grained salient object detection. So this is the full model, but then we add 2 special attention modules, or known as SAM, to refine the early encoder layers. So and we apply independent loss functions to all these ends. The idea is to train the whole model together, and once the whole model is trained, we remove everything else, the decoders and refinement modules, and use one of the shallow encoder branch as a light model on embedded devices. We achieve this comprehensively by 2-step training. On the first step, before training, let's discuss this. So this is our full model. Input goes to encoders, then decoders, and refinement modules, and the output. And this gives us 20 frames per second on 1080 GPU. And this is our light model. So input directly goes to encoder and the shallow branch. And this gives us 21 frames per second on Jetson Xavier, which is equivalent to 86 frames per second on 1080 GPU. And as I mentioned, for training, we pre-train the backbone first with comprehensive terrestrial and underwater images. And then we fine-tune the end-to-end model on underwater images only. We use the traditional cross-entropy loss and the binary localization error term, which we kind of formulated. Please refer to the paper for the detailed loss function formulation, training pipeline, and evaluation pipeline. For the rest of the presentation, we'll just show some qualitative examples and demonstrate how we can use it in practice. For instance, here, the white pixels represent the output of the full model, and the green pixels and the red object contours represent the output of the light model. As you can see, the full model's output is fine-grained and pixel-level accurate, where the light model's output is sort of abstract, but still pretty well localized for high-level decision-makings, and to segment out the background from interesting foreground regions, such as humans, other robots, fish, and coral reefs, and instruments, and so on. This is our model in action on footages of underwater human-robot cooperative experiments. As you can see, it can successfully segment out the water body background pixels and sort of gives you a visual attention modeling, like visual filtering light of kind of job. And as it runs on 20 frames per second, we can use on near real-time applications. The backbone is trained on both terrestrial and underwater images, so it sort of works on random data. We'll show in the next example that on a random style video, it's can also work well and sort of gives you where a human would look at. So this concludes our presentation. I look forward to talk more in our poster session. Our poster number is 18, so I look forward to seeing you there. Thank you.
Okay, so next talk will be given by Thierry Guan from University of Maryland, and he will be presenting TNS.
So hello everyone, my name is Thierry Guan, a PhD student at University of Maryland, College Park. Today I'm presenting my work, TNS, Terrain Traversability Mapping and Navigation System for Autonomous Excavators. The work is conducted while I'm interning at Baidu RAL Lab. Just to give you some background, construction robotics has been a billion-dollar industry. The size of global market of excavators is $44 billion in 2018 and is expected to grow to $63 billion by 2026. Baidu previously developed an autonomous excavation system that can perform excavation tasks for more than 24 hours without any human intervention. And in this paper, we focus on navigation aspects. So we present a real-time terrain traversability estimation and navigation system, TNS, for excavators. We show that our method is the state-of-the-art method on traversability mapping in complex environment. We have integrated TNS with planning and control algorithm and evaluate the performance in real-world setting on an excavator in various challenging settings. We highlight the benefit of TNS in terms of the first autonomous excavator that can navigate through complex, unstructured environments. And in the end, we present a complex worksite terrain dataset in unstructured environment with 7 different classes based on different terrain types, traversable regions, and obstacles. We will release the dataset. So the dataset is collected on an excavator while a worker is navigating through a construction site. We extracted 669 images from 30-minute videos and annotate those data according to terrain types and obstacles. So the perception pipeline of TNS consists of 3 components. So the first component process the RGB image stream and segment the image according to terrain types. The segmentation results are projected onto the 3D space. The second component extracts geometric estimation according to slope and height, step height based on the point clouds. And finally, the semantic information and geometric information are combined to calculate a traversability map for mapping and navigation module. So here are some perception methods that include 3D semantic segmentation methods and traversability mapping methods. We evaluate the final traversability output based on both traversable, non-traversable regions, as well as the mean accuracy of each terrain type. Now we present the proposed TNS. The perception module takes several perception sensors and generates the traversability map that encodes the terrain types and shapes. Next, the planning module takes the traversability map and generates a feasible trajectory. And finally, we use a tracking controller and speed controller to navigate the excavator following the planned path. So we use a high accuracy GPS RTK for localization purpose. So next, we'll show some traversability map generated by our methods. So on the left is the image stream. On the top left is the image stream from the excavator in real time, and on the top right is the generated semantic segmentation result, which is also predicted in real time. At the bottom left shows the colored point clouds after we project the semantic segmentation result onto the 3D space, and the bottom right is the final traversability map. Next, we'll show some planned trajectory based on different mapping methods. On the left is a planning result from a method that based only on geometries, while on the right is the output of TNS. On the left, no viable trajectory are found due to the noisy output of the map. On the right, our mapping methods can find a safe path to the goal. Our method can remove noise from geometric computation and generate a clean map through a semantic segmentation. In this case, we highlight the obstacles on the map with a red circle. The geometric information could identify the geometric information could not identify the obstacles, while we can see the obstacles through a semantic information. So the geometric-based methods would draw a path over the obstacle, while our method can avoid the forbidden region and obstacles. Now we show a clip of excavator navigating in a construction site based on TNS. So there are many technical difficulties that we need to overcome and make the excavator navigate through this challenging terrain. So please refer to the paper for more details. Just as a safe protocols, the human operator has to be in the cabin for all times. And finally, I want to thank everyone for being here today, and thanks all the collaborators. If you have any question or would like to chat, please feel free to reach out. Thank you so much.
Thank you. Next talk will be given by Nathan Hughes from MIT, and he will be presenting Hydra.
Hi, I'm Nathan Hughes, and today I'm presenting Hydra, a spatial perception system for 3D scene graph construction and optimization in collaboration with Yun Chang and Luca Carlone. 3D scene graphs are a promising hierarchical map representation for robotics. In addition to the 3D metric semantic mesh and objects that a traditional 3D reconstruction technique might provide, a 3D scene graph also includes a sparse description of the free space in the places layer, as well as the scene layout and the rooms layer. They've shown promise for both high-level scene understanding, as well as early promise for path planning and reinforcement learning search. However, previous approaches like Chimera, scene graph fusion, and others have had to make trade-offs between scene graph completeness, online operation, and actually correcting the scene graph for noise during scene graph construction. Chimera especially could take up to 30 minutes to construct a scene graph for large environments due to a reliance both on a global voxelized ESDF of the environment, as well as a need to rebuild the scene graph from scratch to actually correct for drift after detecting a loop closure, both of which aren't great if you want to use scene graphs for real-time robotics applications. Instead, we propose Hydra, a parallelized architecture. Hydra ranges between low-level, mid-level, and high-level perception processes. We use VIO for basic localization of the robot, and we piggyback the first two layers of the scene graph off of 3D metric semantic reconstruction. We also have a backend that turns a odometric scene graph into a persistent scene representation. Hydra also includes as contributions a novel room segmentation method that operates directly on the places layer, a novel loop closure detection method that exploits the hierarchy of the scene graph, as well as a method for optimizing the scene graph to actually correct for drift. Next, we show a video of Hydra actually operating in an example scene. We first use Chimera to actually produce the 3D metric semantic mesh inside a spatial window around the robot. We then use Euclidean clustering to actually extract the objects from the mesh vertices inside that active window. We extract the places from a generalized Voronoi diagram that is a byproduct of building an ESDF inside that active window. And finally, we extract the rooms from the places in a process that we describe next. This room extraction process is divided into two phases, the first of which is shown on the left. We filter the places graph at different distance thresholds to simulate dilating the environment, naturally closing off doorways and other openings. This leads to a series of candidate rooms, of which we pick the most persistent. We fill out this candidate with partially seeded Louvain clustering, a community detection method giving us the final rooms. For loop closure detection, we supplement traditional vision-based descriptors that are dbout2 and orb descriptors with subgraphs in the object and places layer, forming a hierarchy of descriptors that we use to actually filter the vision-based matches. We can also register these subgraphs together when vision-based matching fails using point cloud registration techniques, giving us additional robustness. When we actually detect a loop closure, we can then go and optimize the 3D scene graph by building an embedded deformation graph from the robot poses, the mesh control points, which are obtained by spatially compressing the mesh, as well as a minimum spanning tree of the places graph. When we optimize this structure, it's equivalent to pose graph optimization. Here we show example data in MIT student housing. You can see two hallways on top of each other at an angle due to drift, but once we detect a loop closure and actually optimized, the scene graph snaps together, creating a much more consistent scene. Hydra represents a very significant step forward for real-time performance, and we include preliminary results on an NVIDIA Xavier NX, an embedded processor. Note that we also show comparable accuracy to Chimera in the paper despite running in real time. So in summary today, I've discussed Hydra, a spatial perception system that constructs 3D scene graphs in real time. Hydra is capable of actually correcting the scene graph for noise through 3D scene graph optimization and has a method for augmenting traditional vision-based loop closure using the scene graph. Our code is open sourced and released on GitHub. We're very excited about future steps involving improving the semantic richness of the scene graph, and I'm personally looking forward to talking to everyone at our poster session about future applications of Hydra, as well as other technical details. Thank you.
Thank you, that was excellent. So next talk will be given by Andriy Roshev from University of Bonn, and he will be presenting FaDIV-Syn.
Hi everyone, my name is Andre from the University of Bonn, and I will present FaDIV-Syn fast depth independent view synthesis using soft masks and implicit blending. So our work is motivated by an avatar setup on the left where an operator with an head-mounted display perceives the environment through stereo cameras which are mounted on an avatar robot. Due to limits in degrees of freedom and latencies, it might be necessary to synthesize novel views at different camera locations, as you can see on the right. So the main task here is to synthesize novel views given just 2 input cameras from in dynamic scenes in real time. Our 2 main competitors are 3D photo and stereo magnification. On the right, Xi et al. First estimate stereo depth to then build a so-called layered depth image and in-paint disocclusion areas. The main drawbacks are that their method is very slow, that they have to re-estimate the LDI in dynamic scenes, and that they have a strong dependence on depth since they warp using depth explicitly. On the left, Su et al. Then predict the so-called multiplane image from a given plane sweep volume to then render novel views using warping and alpha blending. Their drawbacks are that they also have to re-estimate this MPI in dynamic scenes, that they have limited in-painting capabilities since they built the MPI in the reference camera, and that they also have a strong dependence on depth since each pixel will be assigned to one depth plane. So in our method, we forgo the geometry estimation by building the plane sweep volume in the target camera. We therefore So we built the plane sweep volume in the target camera and therefore forgo the geometry estimation. And a single CNN then learns to propagate areas of high correspondence to the output image directly. We mark these in green. In the lower figure, we show blended corresponding planes where such areas occur as sharp regions. These you can see in the green circles. The network should also learn to discard poorly corresponding areas, which are marked in red, and to in-paint disocclusions already at this stage. Our method can handle reflections, transparencies, occlusions, and disocclusions. This I'm going to show in this animated figure, where we also have the blended corresponding planes and the prediction of our network in the lower right. We further extend our pipeline by a so-called soft masking network, which estimates plane-wise masks. We call these soft masks since each plane pairs are considered independently, and thus one image pixel can have multiple high values in different planes, as we illustrated here in the lower figure. The main network then accounts for these masks in a learned fashion using gated convolutions, which eliminate the need for explicit masking operations. Through this gating, the network then might also learn to ignore the mask if beneficial. So we evaluate our method on the large-scale real estate 10K dataset, where we compare our ablations with 32 planes, 19 planes, and without the soft masking called NoSM against our competing methods, stereo magnification and 3D photo. As you can see in the left table, all our methods or ablations outperform our competitors in all metrics. We can furthermore see the benefit of our proposed soft masking. On the right, on an image size of 540p, our fastest variant then achieves up to 40 frames per second, which allows us to render in real time. So on this animated comparison with Su et al., we show that their explicit depth estimation can lead to significant synthesizing errors. As you can see on the right in the circle, the window separation is clearly assigned to a wrong depth plane, which leads to such errors. Our method on the left does not suffer from this problem. In the second animated comparison, I show disocclusion areas, which are correctly inpainted by our method on the left, whereas the method of Su et al. Creates strange stretching artifacts in these regions. I hope you can see that. An example can also be seen in the lower right corner. Yeah, thank you very much for your attention, and if you're interested, feel free to see me at my poster session. Thank you.
All right, last but not least, Jiang Chen from Indiana University will be presenting CALI, and right after this, we'll have the Q&A session.
Hello, everyone. My name is Zhen from Indiana University. In this work, we propose a novel domain adaptation method to help robots better understand the traversability in images. It could be easy to obtain plenty of data in simulators, but it could be very expensive to have data in the real environments. Data is the decisive factor for learning-based methods, but there is usually a non-trivial gap between the data in different domains. In this work, we're targeting at decreasing this gap by proposing a novel and supervised domain adaptation model. In unsupervised domain adaptation, we have a source domain and a target domain. In the source domain, we have images and labels. In the target domain, we only have images without labels. We want to leverage those data to make the model have the inference capability on target domain. Typically, fine alignment is required for dense predictions. Fine alignment means we need to consider to align features of different classes from two domains. But in unsupervised domain adaptation, we cannot detect class features in target domain, as we have no labels here. To align the source features and target features, we first have to train two different classifiers on source domain, which generate two different decision boundaries, F1 and F2 here. The disagreement between the two classifiers is only training force to align the features. We use adversarial training between the feature generator and the classifiers to align the features. An equilibrium between the feature generator and the classifiers is expected to reach. But this is very difficult to reach because the searching space is complex, as we need to predict multiple classes for each pixel. And the training can be very easy to diverge. In this work, we solve this problem by applying a domain alignment as a constraint to the class alignment. At the very beginning, we have a source-only model, which performs poorly on target domain. In the first stage, we perform a domain alignment, which is trying to align the two domains generally. This will decrease the general distance between two domains, but lead to prediction errors, as this coarse alignment does not consider any class features. In the second stage, we perform the class alignment based on the decreased domain distance. To integrate the domain alignment and class alignment, we propose a pseudo-trilateral structure where both classifiers and the domain discriminator are trying to adjust the feature generator. Here is how we train our model. During training, we first perform a supervised training using source labels. Then we maximize the distance between the classifiers, as we expect to have two different classifiers. And next, we perform a domain alignment. And we use a training order of max-min instead of min-max. Last, we align the features in a fine way. We repeat the 4 steps until the maximum iteration is reached. We have also proved in theory that the domain alignment can be a useful constraint for the class alignment, which is consistent with our intuition. In experiments, we have validated that the training of our CALI model is smooth and efficient compared with the class alignment method. And compared with other baselines, our model shows advantages over other baselines for most of the classes in this city environment, sim-to-real adaptation, and forest environment, real-to-real adaptation. We have also validated that the proposed model is useful in the real navigations. Here, we assign a navigation task for a ground robot in a fall forest, which has a very different appearance than the summer forest in the source data set. The selected environments are particularly challenging, and we have no any label for the images from this fall forest. But our perception model can accurately predict the semantic classes in images and facilitate navigation. We believe our model is useful in the real deployment of the robot because our model can quickly adapt to different domains. Thank you. And if you have any question, please come to my poster, and the number is 22. Thank you.
Okay, so we'll start the Q&A. I will ask all speakers to come ahead.
I have a question for the Hydra paper. So does your scene graph currently consider dynamic objects? And if not, do you plan to work towards that direction? Thank you.
No, we don't actually explicitly consider dynamic objects yet, but that is definitely something we're very interested in for future work.
All right. Thank you.
Yeah, I have a question for TNS paper. Yeah, I just wonder, for this challenging environment, how do you define what is traversable terrain, what is untraversable terrain? Is that kind of human-decided, or what?
Yeah, so that's so basically that's a tricky concept. So basically, we annotate them according to their semantic labels, and then basically, for now, assign a score. So basically, if it's roughly flat, we assign it to, with the low score, while if it's obstacles or bumpy region, we assign it to a little bit higher score. So right now, it's more like a heuristic, but eventually, we want to find some more better criterion to decide what is the best traversability.
Any more questions from the audience? Okay. Then I will ask maybe a few questions. Maybe we start with Tiana. So do you have a mechanism for recovering from classification errors once the robot starts following the planned trajectory?
Yes. So basically, there are some classification errors. So indeed, we're not able to test, extensively on like all different scenarios. We only tested some roughly bumpy scenarios in the real world. But if we want to give a little bit more unconstructed environment, there will definitely be some segmentation error, and we need to deal with that.
And how does the robot deal with that? Let's say, for example, some location is classified as traversable, and there is an obstacle there that was missed by the classification. How does the robot deal with that?
Right. So basically, that's why we use geometric information as well. So there are some cases that can only be captured by geometric information, while some cases can be captured by semantic information. So basically, we collect some data in our work sites. So basically, it can be regarded as, we saved this environment before and we annotate them according to the traversability criterion. And so, so the classification should be relatively accurate. And if it's not, then it can either be detected as from geometric information, or it's just a corner case that we need to handle.
Mm-hmm. Any more questions from audience? Well, if there isn't, maybe I'll ask one more for Hydra from Nathan. So at the bottom level, you rely on semantic segmentation, right? So what if some objects are unknown? You don't have any categories for them.
Then they don't get picked up by the semantic segmentation. But I think we're interested in looking at techniques where you can build in like unknown object categories in addition to the like base 2D semantic segmentation network.
Okay.
Thanks.
Okay, thanks. No questions, so keep asking until somebody comes up with question. So question for Andre. So I was curious about the how much you can generalize outside the input image. Like, is it mostly interpolation between the two views that you give as input, or is it able to predict views that are beyond the interval between them?
Yes, so all the results we show are extrapolation results, so we always go outside.
How much can you go outside, usually?
That really depends on the situation. So if you have only geometry very far away, you can go very far outside. If you're very close to objects, it's obviously a more difficult problem then. So it really depends.
Okay, thanks. Yeah, thank you all. Yeah, so let's thank the speakers again.